All right, so there is where we end the evidence that was added for arguing the theory of plate tectonics. So again, the three different things that we saw that helped coin that theory were hotspots, paleomagnetism, and ocean drilling. All right, so those three definitely going to be tested on. Make sure that you study them and understand. So how is plate motion measured? That's what we're going to cover now. So several methods allow us to establish the direction and the rate of plate motion. These methods allow us to track the motions in paleogeologic time. So this first one is the geologic measurement of plate motion. So from ocean drilling techniques, many rock samples are collected, as we saw before in the evidence for plate tectonics. And if the location of the gathering sample or the gather of the sample is known, as well as its distance from the spreading center, and you know the age of the rocks that are found, then the rate of travel from the ridge can be found, right? So through this method, researchers have made a map like the one you see below in the screen, where the red color represents the newest rocks, and where the thicker the color is, the faster its rate of travel is, basically. So from what you see, for example, the East Pacific Rise, which lies right here, is spreading nearly 3 times as fast as the Mid-Atlantic Ridge, which lies right here. So you see both of them are new type of crust, but you see obviously that it is the bands of color are much greater here in the East Pacific Rise than they are in the Atlantic Ridge. Okay. So these types of maps also provide us with clues of current direction of plate motion. So by examining the transform folds directions that offset the spreading center, so those fracture zones, is how we get those clues for the current direction of the plate movement. And unfortunately, ocean floor is too young. Again, as we saw before, it was only about 180 million years or younger. So the knowledge of past direction and rates of travel can only be done using paleomagnetism of continental rocks. Anywhere, again, older than 180 million years ago can only be done using paleomagnetism of the continental rocks. Another method that is used to check the plate's motion is measuring plate motion from space. So this is done through GPS recordings. GPS stands for Global Positioning System, which uses satellites to pin down the exact position of a site. So to establish plate motions, GPS data are collected at numerous sites repeatedly over a number of years. The map that you see below shows the resulting map that is typically made from that. It shows the directions of the plates, or the direction at which the plates are moving, as well as the magnitude at which it seems to be moving. So for example, the Nazca plate, which is down here, is moving eastward at a very high speed, and the Caribbean plate is moving northeastward at a fairly slow speed. As we saw, for example, in the Yellowstone hotspot case, you see that the North American plate is indeed moving pretty much southwestward. So that kind of confirms our initial hypothesis. So again, you also see, for example, the Pacific plate is now moving pretty much northwestward, also confirming the hotspot hypothesis for the Hawaiian Islands, and it is moving at a very high speed, which is also what I had suggested. Okay, so this is the last slide, so hopefully it shouldn't be too much longer, but it is a long slide. So now we're going to cover what are the current hypotheses that say, what are the mechanisms that drive the current plate motions. So again, we looked at what the plate boundaries are, what the theory of plate tectonics state, what is the evidence to back that theory up, and what are the ways in which we could measure the plate motion. Those are the things that we have covered thus far, as well as the continental drift hypotheses. Okay, so it is generally accepted amongst researchers that some type of convection, which in turn is a type of heat transfer, is the driver for plate motion. So convection in this case states that hot magma is rising and cold, dense oceanic lithosphere is sinking. The details of this convection flow, however, remain a topic of debate, and we'll cover a little bit of that debate later on in the slide. So, although the mantle consists almost entirely of solid rock, it is hot and weak enough to exhibit a slow, fluid-like convective flow. As you can think of convection as what goes on inside a pot when you're melting water, for example. The heating at the base of the pot near the stove warms the water next to the base, making it warmer and hence less dense and more buoyant, which causes that kind of block of water, if you would, that cell of water, to rise in relative thin sheets or blobs that spread out all the way towards the surface. At the same time, the upper layer of the water is cooling by being in contact with the cool air above. And in turn, it becomes denser and it starts to sink to the bottom of the pot. So, there is a rotation-like behavior going on with warmer packets of water particles, if you would, going up as they get warmer and then coming down as they get cooled again at the surface. So the same thing happens with our mantle, given obviously the clear simplification of the system. So there are two mechanisms that allow for this to happen. The first one is the slab pull, which occurs when the subducting cool slabs of plates in a convergent plate boundary are being pulled downwards into the mantle by gravity and their dense nature, right? And the second mechanism is ridge push, which happens when elevated surface causes a ridge. When an elevated surface that causes the ridge is caused by the rising material from the mantle at a divergent plate boundary. So due to this elevated ridge, the slabs on either side of the ridge basically slide down the flanks of that ridge as gravity pulls on them. So the image over here kind of shows you those two different mechanisms. Slab pull is fairly straightforward. The cool, dense plate is sinking into the mantle, both because of the nature of the plate itself, the cool and dense nature of it, but also because of gravity. And then ridge push happens when you have divergent plate boundaries. You have hot rising magma, which pushes the surface to be elevated. And so the sides of the two plates that are spreading apart kind of slide past downward in the flank of that ridge. So it is thought, however, that slab pull mechanism has a lot more influence in this plate motion, and this is based on current plate motions associated with convergence zones. So if you take, for example, the Pacific, the Cocos and the Nazca plates are moving at a very fast speed and are greatly associated with convergent plate boundaries. And in contrast, the North Atlantic Basin, for example, has a very slow movement because it is only associated with divergent plate boundaries. So if we go back to the previous slide, again, you're seeing that with convergent plate boundaries that are associated with the Pacific plate, the Nazca plate, and the Cocos, well, the Cocos plate doesn't have a measurement there, but also that plate, you see that the motion appears to be very fast. There's a very fast rate of change. But the motion in near the North Atlantic plates is fairly slow. And this is because it's only associated with the ridge push mechanism, or that's what is suggested, I suppose. So although there is a consensus saying that convection is the main driver of plate motion, there is still disagreement between scientists about what specific types of convection occur in the interior of the Earth. There are two different models that have been made towards a convection model. The first one is the whole mantle convection model, and the second one is the layer cake model. So the first model that you see on the left hand side of the image below, it suggests that cool, dense slabs, as we know them, the slabs that are subducting into the mantle, sink as far as the mantle core boundary, so all the way to down here, and hence drives the hot lower portions of the mantle all the way up through rising tube-like plumes, or through mega plumes, as you're seeing. So these are the hot-like plumes, cylindrical-like, tube-like, and these are the mega rising plumes that are suggested, and the slab sinking all the way to the mantle core boundary. The second model is the layer cake model that you're seeing on the right side of the image, and it suggests that the Earth has two largely disconnected convection layers, a more dynamic upper layer driven by the descending slabs of the cool oceanic lithosphere, just like we saw in the previous model, but only going so far. So this slab only sinks somewhere between 660 and 1,000 kilometers in depth, is what is thought based on this model, but not any more than that. And then that would be the upper, more dynamic layer, driving that high convection, I guess. And then there would be a lower layer beneath that all throughout the rest of the mantle that is much slower and more sluggish, that carries heat upward without very much mixing of the layer above. So the model is still being debated, but the mechanism is agreed upon scientists and upon the larger community as well. Okay? So convection is the main mechanism, the main driver. How it works inside of the interior layers is not exactly, determined and agreed upon. So with that, we conclude Chapter 2 on plate tectonics. I hope it was useful. It is a very key chapter to understand all the coming ones, so I strongly recommend that if you didn't understand some of it, you go back and rewind and make sure that some of those terms and some of those mechanisms are better, you understand them a little better. And again, just as always, you're encouraged to ask me any questions that you have about this.